A curved section of a highway has a radius of curvature of r. The coefficient of friction between standard automobile tires and the surface of the highway is mu. A. Draw and label all the forces acting on a car of mass m traveling along this curved part of the highway. The car represented here with the force of weight is acting down because that is where gravity is pulling. The normal force is upward because it is the force of the road pushing against the car. And the force of friction is inward toward the center of the circle because otherwise the car would go flying off of the track. B. Compute the maximum speed with which a car of mass m could make it around the turn without skidding in terms of mu, r, g, and m. We know that force of friction is equal to the centripetal force because in the diagram it was the one pointing inward toward the circle. Centripetal force is equal to mass times centripetal acceleration. So, force of friction is equal to the mass times centripetal acceleration. Centripetal acceleration is equal to v squared over r. So, force of friction is equal to mv squared over r. We also know that force of friction is equal to mass times gravity times mu. So, in the end, we know that mass times gravity times mu is equal to mv squared over r. The m's cancel out, and the r is multiplied to the other side, so that we have v squared equals r g mu, which means the maximum velocity is equal to the square root of r g and static mu. City engineers are planning on banking this curved section of highway at an angle of theta to the horizontal. Draw and label all of the forces acting on a car of mass m traveling along this bank turn. Do not include friction. So, to draw this, we know that the car must be on an incline. The force of weight still acts straight down, but the normal force is perpendicular to the plane, and force of friction is ignored. D. The engineers want to be sure that a car of mass m traveling at a constant speed v, the posted speed limit, could make it safely around the bank turn even if the road were covered with ice, that is, essentially frictionless. Compute this banking angle theta in terms of r, v, g, and m. So, the first thing that we need to do is to add the components of the normal force. So, here we have our diagram from before with the added forces. We have added in the angle of theta, the vertical normal force, which is normal force times cosine of theta, and the horizontal normal force, which is normal force sine of theta. And we also have added in the direction of the centripetal acceleration. From this, we know that there is no vertical acceleration. So, we know there is no vertical net force. That means that the normal force times cosine of theta, that being the vertical component, minus force weight is equal to 0. So, the normal force times cosine of theta is equal to the force of weight. The force of weight is equal to mass times gravity. So, the normal force cosine of theta is equal to mg, which means the normal force is equal to mg over cosine of theta. Now, we know that on the horizontal end, the normal force times sine of theta, that being the horizontal component, is equal to the centripetal force. The centripetal force is equal to mass times the centripetal acceleration. And centripetal acceleration is equal to velocity squared over r. So, the normal force times sine of theta is equal to mv squared over r. Then we substitute in our answer here for normal force into this equation with normal force in it. And we have mg over cosine of theta times sine of theta is equal to mv squared over r. The m's cancel out, and the sine over cosine becomes tangent, making the equation g tangent theta is equal to v squared over r. And in the end, we have that theta is equal to arc tangent times v squared over g times r.